Hi guys, this is Will from Group 3, and we're going to be looking at the Mythbusters episode where they look at the effects of swimming in syrup. Right? And we're going to apply Newton's law of viscosity on this scenario. So the learning objectives are to apply the conservation of momentum to analyze forces acting on a swimmer moving through a viscous fluid, and to use Newton's law of viscosity to relate velocity gradients to shear stress in a fluid, to develop a shear momentum balance to derive the velocity distributions near a moving surface, and to determine the shear force acting on a surface and relate it to the thrust and drag forces. Lastly, we're going to perform a force balance between the propulsion and the drag to predict swimming speed. Now, the question here was, does swimming in a thicker fluid make you faster or slower? A pool was thickened with gargum to approximately 2 times the viscosity of water, and what they observed was no significant difference in speed was recorded between the two fluids. And this raised a new question: why does viscosity not affect swimming speed? Which we're going to prove using the Newton's law of viscosity. So the assumptions on the fluid was there was a no slip boundary between the swimmer and the media, and swimming was at a constant speed, approximately 1.5 meters per second. The swimmer is assumed to be a rectangular flat parallel plate so that we can model the shell balances on the swimmer. And also, the media is a Newtonian fluid, and there is steady state or laminar flow. And we did not consider the edge effects at the front or rear of the corners of the swimmer. And lastly, we assume that momentum transport occurs only in the x direction. And the assumption that we made on the swimmer is the swimmer is submerged about a third of a meter into the fluid, and also the swimmer is not distracted by swimming in non-water. So, taking the assumption that the swimmer is a rectangular object in the fluid, we performed some shell balances on it in the z, y, and x direction, and we had the combined momentum transport for each and every direction of the. We postulated that the velocity in the z direction is dependent on the x, and the velocity in the x and y direction is equal to 0, and the pressure is also dependent on the x direction.
Hello everyone, my name is Panache and I'll be walking you through the closed form solution. So here we set up a Z momentum balance on a differential fluid shell which is shown here, and we have momentum in the x direction which enters the shell at x is equals to 0 and leaves the shell here at x is equals to x plus delta x, and the rates are represented here in green. And we also have a momentum in the z direction which enters the shell at z is equals to 0 and leaves at z is equals to L, and the rates are also represented here in purple. So since we have postulated that we don't have velocity in the x direction, that is why this term falls out. And also, since the velocity in z does not vary with z, also this shear term also falls out. So now the question is, why don't we have a momentum in the y direction? So because also there's no velocity gradient in the y, so the momentum transport is in y becomes 0. So this term becomes 0, and also since we don't have a velocity gradient in y, this term also becomes 0. And another question would be, why don't we have the gravitational force in this case? So the reason why we don't have a gravitational force is because we have assumed that our body, the body in question, is horizontal. So we have a 90 degrees angle. So if we do cos 90, we get a 0. That is why we don't have a gravitational force element here. So now we take the Z momentum balance for the shell, and the general expression is the rate of momentum in minus rate of momentum out plus force of gravity is equals to 0. So we include the Z momentum entering and leaving in the x direction, and also the Z momentum entering and leaving in the z direction. So after that, we factor out the areas, and we get this expression, and then we divide by volume, and we take the limit as the thickness approaches 0. And after we have done that, we see that the second term vanishes. So you can try to think why it vanishes. So the reason why it vanishes is because pressure entering here is the same as the pressure exiting here at Z is equals to L. And also the convective momentum flux entering at Z is equals to 0 is the same as the convective momentum flux exiting at Z is equals to L. So these expressions are equal, cancels out. From this expression from the previous slide, when we took the limit as the thickness approaches 0, we find that the derivative of the combined momentum flux is equal to 0. But since the combined momentum flux is equal to the shear stress, we can also say that the derivative of the shear stress is equal to 0. So when we integrate this with respect to x, we find out that our shear stress is a constant, and when we apply the Newton's law of viscosity, we are able to find the velocity gradient, and when we integrate again with respect to x, we are able to find the velocity profile. So now we apply the boundary conditions. So at the swimmer surface, we use the no slip condition. So Vz of 0 is equals to U sub W. And far away from the swimmer, the fluid is stationary. So Vz of delta is equals to 0. So from this, we find out that our C2 is equals to U sub W. And if we substitute C2 here, we found our C1 is this expression here. So this is the final expression for the velocity distribution, and here we have our expression for the shear stress. So if we look at this expression, can you see something? So this is now giving us the relationship between the shear stress and the viscosity. So from this we can tell that the fluid with more viscosity produces greater resistance to motion. So in our case, the syrup produces greater resistance to motion. So next, we now calculate the force acting on the swimmer surface. So since shear stress is force per unit area, we integrate the shear stress over the entire body. So because our shear stress is a constant, we move it out here, and our integration simply give us W and which is width and length, and this would be the final expression for our force.
Now that we know how to calculate the force being applied onto the fluid and by the person, let's put this into action. So we've got the force propulsion. This is from the surface of the swimmer onto the fluid, and they're moving at this steady velocity. They've got a shear layer thickness dp and a surface area between the swimmer and the fluid that they're swimming through. And so when we take the shear stress, this is the viscosity of this particular fluid, times the velocity of the swimmer, divided by the thickness of the layer that we're looking at, and we're multiplying this by the area of the swimmer. This gives us like a force per unit area. This gives us our area. This is that total applied force of propulsion by the swimmer. We then look and see that the forces of drag are very similar. We've got force of drag equals that same viscosity, this speed of this fluid that we're swimming through, the the distance of the fluid that, or not the distance for that we're swimming through. This is the thickness of fluid below the swimmer, and again, this is that area that of the swimmer that multiplies this unit area um, to scale up to the size of the swimmer. If we are swimming at a steady state, the forces have to be balanced. We've got the force of propulsion is equal to that drag force. So take a second, draw out the equations and see what might cancel out. Hopefully you grabbed in both of these equations and saw that the subscripts prevent us from completely removing everything, but we can see that this is largely dependent on the viscosity of this fluid. Those will cancel out from no matter what fluid you're using. Speeds will change. The force imparted in these fluids and that layer of thickness, but you know, everything else changing, this viscosity term will always cancel out. And here we're solving just for that speed of the drag force on the surface of the body, and we have this term where we're rearranging this equation just to solve for u, and mu is not needed in this final expression. Speed is independent of viscosity. Take another second and think about where this model might break down. So this model begins to fail at extremely low viscosities, while practical limitations also arise at very high viscosities, where most swimmers would tire very quickly and wouldn't have the strength to swim through extremely viscous fluids like pitch. And this is setting aside worries of like stickiness of the fluid, pulling on your skin or hair, worrying about breathing. Versus with extremely low viscosities, like when walking through air, the flow regime of the fluid around you becomes way too turbulent for this laminar flow model. So this model breaks down. We can also solve this problem with a open form solution. So for this, we're reintroducing all of the numbers from the height, the width, and the depth of the swimmer. In this case, we have someone who's 2 meters tall. They're just over a third of a meter wide and an eighth of a meter from front to back. And again, we're assuming this swimmer is submerged, third of a meter. They're this rectangular prism. We're going to ignore the shear stress on these corners, where the shear stress from the top will interact with the shear stress on the sides of the body, as well as we're neglecting this front and the back, this pressure of the swimmer swimming forward. We're just going to assume these are canceling out. We want to keep this in the laminar flow regime, and we're holding the previous assumptions where this is a Newtonian fluid. Here we already have calculated the areas for the sides of this swimmer, because when we calculate the force, we need the shear stress, which is is going to make this unit area force, and we need to multiply it by that area. The viscosity of water, this is like the basis that we're comparing all the other swims to. The Gargum solution that Mythbusters used, which had twice the viscosity of water. And then we also want to throw in, maple syrup from Canada standards, significantly thicker, swimming through maple syrup. So in this example, we're swimming at 1.5 meters per second. We are looking at increments of shell balances of a centimeter, or a hundredth of a meter away from the swimming body. And again, we have our viscosities down here and our areas up here. And we can't realistically measure from the swimmer all the way down to the bottom of the ocean. If you draw the profile of shear stress as you get a further and further distance from the body, you'll note that each shell contributes less and less force of drag onto the body. So we only want to look to where, say, 99.5%, or whatever your tolerance is for your problem, to the swimmer. This distance again is incrementing by a hundredth of a meter, as it extends out from it. And then we're multiplying it by 0.05, which is both sides of this body. The top, the 0.7, which is this, we're only extending out a third of a meter. And then again, the bottom, also 0.7 square meters, which we need to extend out until each additional increment of 1 centimeter applies less than 0.5% of the total shear stress for that side. Take a second or two to work through shear stress profiles for the open form solution approach, looking at the water and syrup. And feel free to initially just set an initial distance of the 0.33 meters. See if that's a good stopping point for the sides and the top. If not, you'll get a close approximation for starters. Try imagine what these shear stress profiles look like for syrup, gargum, and water. comparing that water, guard gum, and shear force, whichever you decided to look at, hopefully you came up to something with a profile similar to this. With water, we start out with a profile that starts at approximately 15 newtons, and on that first centimeter away from the body, and in that second centimeter shell away from the swimming body, we've already dropped below 0.1 newtons of force, and we go all the way down to 0.08, and then we drop even further down to 0.05, versus in Gargum, which had twice the viscosity. You see that we have just over that 30 or zero point 0.3 newtons of force, and then by that second shell away, we drop right next to that 15. This is actually the same value we see for that first or data point in that first shell. And then by the third shell, we're seeing we follow this exact same pattern for water, and each incremental shell, and found where we start adding less than 0.5% to the shear for each side. You'll note that it was at 0.45 meters that we're no longer contributing significant shear drag from the fluid onto the swimming body. The syrup was significantly more viscous. We're talking 2 orders of magnitude more viscous. So we actually have to go over to this gradient over here and see that we're starting just a little bit over that 30 newtons of force, which, again, we're going from, 0.3, 3, 30. That's our 2 magnitudes. Difference. We drop down and we're about at that 15. This is very similar to here. And I just want to show that this, the amount of shear stress per shell between the swimmer and the fluid is linearly proportional to the viscosity of the fluid. Summing up under all of these, or taking the integral under these curves, in this case, we'd only go out to the 0.45 meters out here. Because otherwise this curve could go on forever, and we'd have how much drag force each fluid is imparting on the body. Thank you for watching our video, and we look forward to seeing your questions in class. Thanks.